Okay, so good afternoon, everyone. I'm Shivani Dhok, and I welcome you all for the summary session for this course of Principles of Signals and Systems. So this is the last lecture from my end, and today what I'll do is do week, I'll do a recap of the content in week by week sense, like from the week 1 to week 12, whatever things were covered in that particular week. I'll discuss them in not great detail, but to somewhat detail so that it's a revision for you and you can go back to your notes and then look at those questions that we have solved during all those 12 weeks or the content that was covered in the recorded lectures available on the NPTEL portal. Okay, so let's start with the week 1. So week 1 was some sort of an introductory week in which we looked at the two basic quantities of this course, that is signal and system. So what is signal? So signal is essentially a physical quantity that conveys information about some phenomena that is occurring in nature. Or in other words, the signal it is a function of some variable, some independent variable that captures some information about some phenomena. A simple example of this particular signal is your voice signal. So your voice level or your sound level, volume and all those things, how it changes as a function of time is basically your voice signal. Now, the whole course was how to process these signals to get some information or to process or to change some properties of that particular input signal, and that is done with the help of something known as system. So a system basically processes your signal to get some meaningful output out of it. Few examples of systems are your noise cancellation systems. These noise cancellation systems are basically your high pass filters. Then you have amplifiers. Then you have your image denoising or your filters that you use to denoise your images or enhance the quality of your images. Everything comes in the class of systems that basically processes whatever input you give to that particular system, and it gives you some sort of output, which is again a signal. So basically a system will take input as a signal and will give output as again a signal. And we looked at different types of systems. We'll come to that in a moment. But before going there, we looked at different classifications of your signals. So the first classification that we looked at was based on the nature of your independent and dependent um, variables. So when you have a continuous time signal, it means that if you take any time axis and you look at 2 points, let's say T1 and T2, and between these 2 points in this range, if you arbitrarily pick any time instant, let's say this, you will be able to define the value of your signal here. So signal is defined in this particular range. When you have a discrete time system signal, then the signal is defined only at some integer values. So if you look at this particular point, the signal is not defined here. So these are discrete time signals. Then what do you mean by analog? Analog means you have continuous in time as well as continuous in uh, amplitude, and digital is discrete in both amplitude as well as time. Then we looked at another class of signals. We just looked at those classification in the first week. We looked at what is a periodic signal. So if a signal repeats itself after some capital T duration, then it is referred as a periodic signal, and it happens for every integer multiple of t as well. So this is if this particular relation is there, then we have a periodic signal. Otherwise, it is known as aperiodic signal. Then we looked at deterministic and random signals. A signal is deterministic if you can easily interpret what based on some mathematical formula, or you can, given some sense, you can easily tell what exactly will be the value of that particular signal at some given time instant t. Random is you can't predict what a particular value it will have. Then you have symmetry based classification. So symmetry based classification says that a signal is an odd signal if x of minus of t is minus of x of t, and a signal is an even signal if x of minus t is equal to x of t. And the last kind of classification that we looked at was an energy signal. So a signal, if it has a finite energy, then it is an energy signal. If it has a finite power, then it is a power signal. After that, we looked at some different, um, some special kinds of signals. Or functions for that matter. So first we looked at continuous time. In that, the first one is your unit step. So how do you define the unit step function? So it is u of t, which is equal to 1 for t greater than or equal to 0, and it is 0 otherwise. Then the other one is unit impulse. For that, we first looked at a signal which is something like this, delta epsilon t, which is equal to 1 by epsilon for t in the range of minus epsilon by 2 to epsilon by 2, and it is 0 otherwise. Then your unit impulse is delta t, which is equal to limit epsilon tends to 0 delta epsilon of t. And we looked at the various properties of this signal. The first one is if you have any signal x of t and you multiply it by an impulse which is located at t equal to t naught, this is equivalent to x of t naught. So that impulse will pick that particular value into delta t minus t naught. Second, delta a t is 1 by magnitude a delta t. And third one is the shifting property. There is integral minus infinity to infinity x of tau delta t minus tau d tau. It is equal to your x of t. And more importantly, the area under this particular signal is 1. So integral minus infinity to infinity delta t is equal to 1. Then we looked at the counterparts of the signals for discrete time. So again, you have your unit step. So your u of n is equal to 1 for n greater than or equal to 0, and it is equal to 0 otherwise. and the second one is your unit impulse. So this delta n is equal to 1 for n less than or equal to 0, and it is 0 otherwise. So these are few things that we looked at in the first week, which are related to your signals. We looked at classification of signals and all those things. So once we looked at signals and understood various kinds of signals, then we moved on to something known as a system. So what is a system? A system is some function that takes an input and applies this operation given by this t to get output y of t, which is equal to t of x of t. Some function. Okay, and then we started to look at different properties or classification of these systems. So the first classification that we looked at was memoryless. So system is memoryless if its output does not depend on any past or future values of input. So output does not depend on past or future input instances, input values. And the second classification that we looked at was causality. So system is causal if the current value of output depends on current or past input values. And more importantly, there is no future dependency. Okay. Then we looked at other classes of systems, in which we looked at the first thing that we looked at was a linear system. And linear system, as we mentioned during the discussion, it decomposes or it is composed of two different properties. The first one is additive property. So in order to understand that, let's say you have a system. Let's say you have this particular system that we wrote here, and if we give it as an input x1 of t, it will, let's say, give me an output as y1 of t, and if I give input as x2 of t, it will, let's say, give you output as y2 of t. So system is linear if it is both additive and homogeneous. So what do you mean by additivity? So additivity means that if I give input x1 of t plus x2 of t, then its corresponding output will be equal to y1 of t plus y2 of t. And system is called homogeneous if I give an input c into x1 of t, then my output will be equal to c into output corresponding to x1, that is y1 of t. Note that this constant c should be same. There shouldn't be any change in this constant. So in this situation, if this is the relation that you get, then in that case, your system is homogeneous. And when a system is both additive and homogeneous, it is a linear system. You can combine these two properties, whatever we wrote, into one equation and say that a system is linear if the linear combination of input results into a same linear combination of output. So A into y1 of t plus b into y2 of t. So this constant A should be same. Similarly, this constant B should be same. Then the system is known as a linear system. Then we looked at another class of systems that is known as time invariant systems. So system is called time invariant if shift in input, that is x of t minus t naught, results um, in the same or shifted output, shifted by same unit, same time difference. That is y of t minus t naught. So x of t minus t naught should give you some output, and if you let's say your x of t, when you have x of t as an input, you get y of t as an output, and you shift that y of t by a unit or by a time instant or time t naught, then these two outputs should be same. Then we looked at another thing that is known as your Bibo stable systems. So what do you mean by Bibo here? It means bounded input, bounded output. So it says that a system is Bibo stable a system is Bibo stable if for all the bounded inputs the output is also bounded. That is, for all x of t such that magnitude of x of t is less than or equal to some bx, which is less than infinity, the output y of t has magnitude of y of t less than or equal to some by, which is less than infinity. Then your system is Bibo stable. Then we looked at something known as feedback systems. It means that along with input, you also feed back some delayed versions of your output to stabilize the system and all those things. Then we looked at another class of systems that is linear and time invariant system. So a system is linear and time. When a system is both linear and time invariant, such a system is known as LTI system. And LTI system is the class of system that we studied throughout the duration of this course, which includes the class of filters and all those things. And this linear and time invariant system has a very unique property which says that this particular system can be completely characterized by its impulse response. And what do you mean by impulse response? So let's say you have an LTI system and you give unit impulse as an input, then this h of t is the response of your system to this unit impulse, and that's why it is known as impulse response. And with the help of this particular with the help of this impulse response, we can obtain the output corresponding to any input given to this LTI system. So if you have an LTI system with impulse response h of t, and if you give an input as x of t, you look at its output as y of t, that will be equal to x of t convolved with h of t. And if you have an discrete system, so that will be equal to x of n convolved with h of n. Okay, so what is your convolution? Let's first focus on your okay continuous time signals, continuous time systems. So continuous time convolution for that matter. So this y of t is x of t convolved with h of t. This is equal to integral minus infinity to infinity x of tau h of t minus tau d tau. This is your convolution operation, and this can be achieved with the help of four operations. So the first operation is flip the impulse response, that is get h of minus tau. Then shift your impulse response by a unit t, so h of t minus tau. Then multiply it by x of tau, so you will get x of tau into h of t minus tau. And finally you have integrated, so integral minus infinity to infinity x of tau h of t minus tau d tau. So your convolution operation can be summarized in four steps, that is flip the impulse response and shift it by t units, multiply your and your flip shift impulse response, and then finally integrate it. This is how you are going to get your convolution operation, and we saw many examples of this particular thing in the lecture. Then we looked at different properties of convolution. The first property that we looked at was this commutativity property. So it says that if I take x of t convolved with h of t, this is equal to convolving h of t with x of t. Then the other property that we looked at was associativity. So this property says that if I convolve x of t with some system h of t, and then this is convolved with another system x2 of t, this is equal to x of t being convolved with h1 of t convolution h2 of t. This is the associativity property. And the last property that we saw for this convolution is distributivity. So when you convolve x of t with addition of two impulse responses, this is equal to x of t convolved with h1 of t plus x of t convolved with h2 of t. So this particular thing, associativity property, gives you an idea of your cascade representation, and distributivity property gives you an idea of your parallel system representation that we saw in the last lecture. Okay. Then we looked at these continuous time systems, how to associate the various properties of these continuous time systems to its impulse response. So we said that if a system is memoryless, then its impulse response takes a form h of t, which is equal to some scaled version of your unit impulse, that is delta t. Then we looked at other three properties. Other properties, like the first one is your causality property. So a system is causal if h of t is 0 for all t less than 0. It is non-causal if there exists a t less than 0 such that h of t is not equal to 0, and anti-causal h of t is 0 for all t greater than 0. And then we looked at the Vivo stability equivalence. So it says that a system is stable or Bibo stable if it is absolutely integrable. That is integral minus infinity to infinity magnitude of h of t dt should be less than infinity. If this is satisfied, then your system is stable. And finally, we looked at another interesting concept of eigenfunctions and transforms. So we say that if you have input as e power j omega t, then its corresponding output will be equal to h of omega naught into e power j omega naught t, and this is equal to integral minus infinity to infinity h of t into e power minus j omega t omega naught t dt, something like this, or for the matter tau not t. Yeah, so this is what we get, and this h of omega naught is known as the transform of your system, and e power j omega naught t, it is known as the eigenfunction. Then we looked at the differential equation representation of your LTI system and its equivalence to your linearity and time invariance properties. And then we moved on to look at something known as your discrete time LTI systems. So, similar to your continuous time LTI systems, you can have a discrete time LTI system that will give me an output y of n, where this is, let's say, LTI. And if your input is delta n, then you will get an output as h of n, where h of n is basically your t of delta n. And this is your impulse response. Now again, any y of n can be written as or obtained by convolving x of n discrete time convolution with h of n, which is equal to summation k running from minus infinity to infinity x of k into h of n minus k. Again, the properties that we saw for this particular for continuous time convolution hold even for your discrete time convolution. It is commutative, it is associative, it is distributive. So all the three properties of convolution hold even for your discrete time convolution. Then we looked at again the same three properties, that is memoryless system. So system is memoryless if your h of n is of the form of some a into delta n. It is causal if your h of n is 0 for all n less than 0. All the same properties, whatever we saw, copy paste, it holds, other than your absolute integrability. And for stability, your system now should be absolutely summable. So h of n should be absolutely summable. Or in other words, summation n running from minus infinity to infinity, magnitude of h of n should be less than infinity. Then similar to your eigenfunction and transform for your continuous time systems, we looked at eigenfunction and transform for your discrete time system, but eigenfunction of for this particular thing is Zn, and the output for this will be Zn into h of z, where h of z will be equal to summation k running from minus infinity to infinity h k into z to the power minus k. Okay. Yeah. And then we looked at the difference equation representation of your system, which is something like this. So you can write summation k running from 0 to some m a k y of n minus k. And write it as summation L running from into x of n minus L. And yeah, this we saw. So this is all about your introduction to signals and systems, its classification and all those things. And this was the fundamental or the basic things that were required to build upon the more important things that were about to come from week 4. So from week 4, we started to look at a different representation of these signals and systems by transforming them to some different domains. And that transformation to some different domains gave us some insights into insights about this particular system in some different perspective. And that perspective was with respect to the frequency components present in that system. So the very first transform that we looked at in this course was Laplace transform. This Laplace transform is given for a continuous time signal. So when you have, let's say, a continuous time signal, x of t, then its Laplace transform is, let's say, given by capital X of s, and along with that, this particular function is associated with something known as a region of convergence or ROC. First, let us look at what is your X of s. So for a given X of t, your X of s is given by integral minus infinity to infinity X of t into e power minus st dt. Okay. Now this particular function or expression, whatever we wrote, is an integral. So this integral can either converge or diverge. Now in a particular region of your S, if this integral diverges, it is not going to tell me anything. It is infinity, it is not going to give me any information about this particular signal. So therefore we are only interested in those values of S in which this particular integral exists, or a region of S in which this particular integral converges. And that is known as your region of convergence. So your region of convergence let's say R is a set of values of S such that X of S converges. For example, when we were looking at examples in our class, we looked at exponential signals. So we looked at e power minus at ut, and we said that this particular thing has a Laplace transform as 1 upon s plus a with region of convergence as real part of s greater than greater than minus a. Similarly, when we looked at minus e power minus at into u of minus t, then this particular thing again has a Laplace transform as 1 upon s plus a, but now its region of convergence is real part of s, which is less than minus a. Okay, so this region of convergence is that value of s in which this particular integral exists. Otherwise, it diverges or it goes to infinity. Then, after looking at this particular concept, we first looked at different properties of different properties of Laplace transform, and then we looked at different properties of the region of convergence. Okay, so let us first look at the properties of Laplace transform. So for that, let's say you have a signal x1 of t and its Laplace transform is x1 of s, capital X1 of s, with region of convergence R1, and you have another signal x2 of t with Laplace transform as x2 of s, and region of convergence is R2. Then the first property is your linearity property. So a1 x1 of t plus a2 x2 of t will have a Laplace transform as a1 x1 of s plus a2 x2 of s, and region of convergence will be at least R1 intersection R2. By addition, there might be some pole zero cancellations, so your region of convergence can at max increase, it can't go down. And it can go less than R1 intersection R2. Then you have another property, that is your time shift property. So x of t minus t naught will have a Laplace transform as e power minus s t naught into x of s, and region of convergence remains as R. For that matter, let's take x1. Then you have shift in s domain. Like we had shift in time domain, you will shift it in s domain. So e power s naught t x of t minus t naught. So this sorry this will have a Laplace transform as x1 of s minus s naught. Now your region of convergence is R plus your real part of s naught. Then we looked at another property, that is differentiation in time, which we used a lot. So when you have d dt of x of t, its Laplace transform is s into x of s, with region of convergence as R, and yeah. And if you had a pole at s equal to 0, then that gets cancelled. Then we looked at differentiation in s. So when you have t into x of t, its Laplace transform is minus s into d ds of x of s. Region of convergence is at least R. Then integration in time, integral minus infinity to t x of tau d tau. Sorry. This has Laplace transform as x of s by s. Region of convergence is R, but excluding 0. And the last and the most important property is your convolution in time property, which basically helped us to look at or interpret the system representation in the Laplace domain. So x of t convolved with x2 of t. This has a Laplace transform as x1 of s convolved with x2 of s, with region of convergence at least R1 intersection R2. These were the properties that we looked at. And after that, we looked at another concept. So poles are values of s such that x of s is equal to, first let us look at zeros first. So this is the set of s such that your x of s is equal to 0, and then you have poles. It is the set of values of s such that your x of s tends to plus minus infinity. And then we moved on to look at properties of region of convergence. I'll list them in few moments. But before that, let me just make a note of inverse Laplace transform. So inverse Laplace transform has some formula, but we didn't look into it. We said that instead of looking at that contour integral and all those things, what we'll do is we'll use partial fractions. And get it in standard form. Get x of s in some known form and use standard Laplace transform. So in that particular week, or rather week 4 content, if you go back and look at my notes, I have listed down Laplace transforms of few important signals which you need to memorize in case you get some questions related to this in your exam. So you need to do that, otherwise you won't be able to solve or find inverse Laplace transforms and all those things. And then let us quickly move on to the properties of your ROC. So the first property is it does not contain poles. Second is, for a finite duration signal, ROC is entire S-plane with zeros or poles at plus minus infinity or 0. So this is 0, this is poles. Then if you have a right hand sided signal, ROC is rightwards of rightmost pole. That is, if you have a signal which is something like this, then its region of convergence will be something like this. Then if you have a left hand sided signal, then ROC is leftwards of leftmost pole. And finally, if you have a two-sided signal, then ROC is a vertical strip. Then using these properties of ROC and the convolution property, we looked at Laplace transform of LTI systems. So we know that the output of an LTI system is given by the input convolved with h of t. Then if I take Laplace transform, then y of s, which is Laplace transform of your output y of t, is nothing but x of s, which is Laplace transform of your input, multiplied by h of s, which is Laplace transform of your impulse response. With the help of this, we can write capital H of s as y of s by x of s, and this quantity is known as the transfer function. And you can map the causality property and stability property of this particular system, of a particular system, by looking at the region of convergence of this h of s. So when you have a causal system, you remember that your h of t is 0 for all t less than 0, which means that this is a right hand sided signal, which means that it will have a region of convergence rightwards. So your ROC is rightwards. So a causal system will have a rightwards ROC. But now if someone gives you an ROC which looks something like this and says that please tell me whether this particular system is causal or not, you cannot comment by just looking at the region of convergence. For example, if you have a system which is something like this, so this is -1 and it goes like this. This system is also going to have a rightwards ROC. but it is non-zero for some particular, or understanding this particular property, or making use of this particular property. Then we looked at stability. For stability, what was the criteria? The criteria was this particular signal, this particular impulse response should be absolutely integrable, and that translates to something, that is your region of convergence, or ROC, should include the j omega axis. So this is all that was covered related to your Laplace transform, its region of convergence and all those things. So yeah, someone asked me in the last class regarding, can I explain region of convergence for Laplace and Z transform? Is it clear now?
Yes, ma'am.
Yeah. We'll look into the region of convergence corresponding to the Z transform when we discuss Z. But yeah, this is all about your Laplace transform.
Okay, ma'am. Okay, ma'am.
Yeah. Okay. Then let's move on to the next part of this course. Okay, again, you can stop me at any point of time to ask doubts instead of waiting till the last. Okay, yeah. So after looking at Laplace transform and all those things, we moved on to another transform concept, which is a counterpart of Laplace transform for discrete time signals, and that is known as your Z transform. So if you have a discrete time signal x of n, it will have a Z transform as x of z, and again it will be associated with a region of convergence, that is your R. So your x of z is given by summation n running from minus infinity to infinity, x of n into z to the power n, where the z is in polar coordinates, so that is r into e power j omega. Again, before going ahead, I forgot, this s in your Laplace transform is again a complex quantity which will have a real part and an imaginary part. So this omega corresponds to your frequency, and sigma is some damping thing. Okay, and again, region of convergence R is that value of z such that x of z converges. So very similar. This definition of region of convergence is very similar to the definition of your Laplace transforms region of convergence. So it is that value of, or it contains the, or it is a set that contains all those z's for which this summation, whatever we have here, is finite. That is, it doesn't go to infinity or minus infinity. That is its region of convergence, or the region in which your Z transform converges. After looking at this basic definition, again we moved on to look at different properties of your Z transform. The same way we looked at the properties of your Laplace transform. So again we'll have x1 of n with Z transform as capital X1 of Z and region of convergence R1. And we have x2 of n with Z transform as x2 of Z and region of convergence as R2. So all the transforms that we looked at are linear in nature. So linearity property is the first property that we are going to see in any transform that we saw in this particular course. So a1 into x1 of n plus a2 into x2 of n. This has a Z transform as a1 into capital X1 of z plus a2 into x2 of z, and region of convergence is R1 intersection R2 at least. Then have time shift x1 of n minus n naught as a Z transform as z to the power minus n naught into x of z, x1 of z. So this is R with possibility of zeros, sorry, possibility of poles at z equal to 0 because of this n naught or plus minus infinity. Then you have time reversal. So x of minus n will have a z transform as x of z inverse. And region of convergence is values of t such that 1 by t belongs to your region of convergence, that is R1. Then we looked at time multiplication. So when you have n into x1 of n, its corresponding z transform is minus z into d dz of x of z. Then you have your accumulation property. So summation k running from minus infinity to n xk. This thing has z transform as something like this. So you get an additional 0 at z equal to 1. So additional pole at z equal to 1. So you need to carefully look into the region of convergence or revisit region of convergence. And the last one, which is again the most important property of this particular thing, and that is your convolution property. So when you have x1 of n convolved with x2 of n, you get in z domain as x1 of z into x2 of z. Then similar to Laplace transform, we looked at the definitions of your poles and zeros. So we said that if I'm able to write, so I can write this z transform h of z when you have linear representation or rational z transform. You can write it as n of z upon d of z. So zeros are solutions of n of z equal to 0 and poles are solutions of d of z equal to 0. And then we looked at inverse z transform again with the help of partial fractions representation and standard z transforms. That list again you can go back to week 5 tutorial and you will find it, or basically you can find it in any standard either signals and systems or discrete DSP book. And then we have here the properties of your region of convergence. So the first property is no poles in ROC. Second one is for a finite duration signal. ROC is the entire Z plane. With possibility of zeros or poles at 0 or plus minus infinity. Okay. Then right hand sided signal. So this is exterior. So ROC is exterior to the circle with the radius as max of magnitude of poles. When you have left hand sided signal, so ROC is interior to the innermost pole or the circle corresponding to the innermost pole. And when you have a two-sided signal, you have something known as annular ring. So basically, the ROC is between the region of your two circles. So this is all about properties of your Z transform.
Previous slide, please, ma'am.
Sorry,
Previous slide. Just
this
2
one.
minutes. Yes, ma'am. Yes, ma'am.
Yeah. Let me know when you are done. This will be shared with you. You don't have to.
Okay.
Yeah.
Okay, ma'am. Thank you.
Yeah. Then we looked at the Laplace Z transforms for systems. So when you have a system with impulse response, let's say h of n, and you give x of n as an input, then the output is y of n. So again, if you look at the Z transform, then y of z is equal to h of z into x of z. So again, similar to Laplace transform, your h of z is a transfer function and your output is y of z upon x of z. Now similar again, causality, the condition was your impulse response is non-zero only for positive values of n, which means it is a right hand sided signal. So your ROC is exterior to the outermost pole, and it is stable. For stability, your impulse response should be absolutely summable, and that property translates to your unit circle being included in region of convergence. So your ROC should include unit circle. What do you mean by unit circle? A circle of radius 1 should be included in your ROC. Then in the week 6, we continued to look at your inverse Z transform. And for this, we looked at the classical definition of it, which is x of n equal to 1 over 2 pi j integral over a region gamma x of z into z to the power n minus 1 dz, where this gamma is a contour or closed contour in counterclockwise direction such that it encloses all the poles of z to the power n minus 1 into x of z. And then we looked at the transfer function, the inverse Z transform using the general inversion method. So what does this general inversion method say? This x of n can be written as summation I equal to 1 to p residue of z tending to pi of x of z into z to the power n minus 1. So this residue can be found out based on the multiplicity of the pole. That's how many repetitions that particular pole has. So if pi has multiplicity as 1, then this quantity is nothing but limit z tending to pi z minus pi x of z into z to the power n minus 1. And when this pi has multiplicity equal to r, then this is 1 upon r minus 1 factorial limit z tending to pi. This is of z minus pi to the power r into z x of z into z to the power n minus 1. Then this was the end of the topic of your z transform. And after that, we switched gears and we moved on to another set of transforms or series, which is specifically defined for continuous time signals, for periodic signals. So, first thing we looked at was the Fourier series representation for continuous time periodic signals. So, a continuous time periodic signal is have has two prop has some important quantities to be defined as. So the first one is your fundamental period. Let's say it is t naught. So it is the smallest time duration after which signal repeats itself. Then the another quantity that is associated with this fundamental period is your fundamental angular frequency. So this particular quantity is nothing but your omega naught, which is 2 pi by t naught, and your harmonics are basically integer multiple of your fundamental frequency, where this k belongs to the set of integers. Okay, so any periodic signal, any continuous time periodic signal can be written as a linear combination of your harmonics. So x of t, if it is periodic, it can be written as k running from minus infinity to infinity, some c k's into e power j kth harmonic t. And the ck can be obtained as 1 over t naught, integrating it over any period range of t naught x of t into e power minus j k omega naught t dt. So this is your complex Fourier series representation. We looked at the equivalent trigonometric Fourier series representation. So we saw how to get that also. I won't write it in the interest of time. It's there in the notes. We'll be mostly playing with the CKs. And then we looked at something known as your Dirichlet conditions. So these Dirichlet conditions are sufficient conditions. These are not necessary. So these are sufficient conditions for the existence of your Fourier series coefficients. So if a particular signal is absolutely integrable over a period, if it has finite number of maxima and minima over a period, and if it has finite number of finite discontinuities in a period, then it will have, or its Fourier series coefficients are bound to exist. If any one of these three conditions is not satisfied, we cannot say whether the Fourier series coefficients are going to exist or not, because this is a sufficient condition. This is not a necessary condition. When these conditions get satisfied, we can say that definitely Fourier series coefficients are existing. However, if these conditions are not followed, we don't know. It may exist or may not exist. Then we looked at another concept, that is the power of periodic signals and the theorem associated with it, which is basically your Parseval's theorem. it says that your power 1 over t naught integral over t naught magnitude of x of t whole square dt. This is equal to summation k running from minus infinity to infinity magnitude of ck square. This is your Parseval's theorem. So after that, we looked at, so we discussed these for frequency domain representation for periodic signal, for periodic signals. Now, what if this x of t, this continuous time signal, is not periodic but it is an aperiodic signal? Then for aperiodic signals, we define something known as Fourier transform. So when you have an aperiodic x of t, it has a Fourier transform x of omega associated with it, where this x of omega or capital X of omega is given by integral minus infinity to infinity x of t into e power minus j omega t dt, and you can recover back your x of t as 1 over 2 pi integral minus infinity to infinity capital X of omega into e power j omega t d omega. Now again, similar to the existence of your Fourier series coefficients, you have conditions, Dirichlet conditions, that is again your sufficient conditions for the existence of Fourier transform. So the first is the x of t should be absolutely integrable. Next, it should have finite number of maxima and minima in any finite interval, and then you should have finite number of discontinuities in the signal. Then it has a relation with your Laplace transform. So remember, your Laplace transform S is in your Laplace transform, your S is basically sigma plus j omega. So if you have sigma equal to 0, you will get x of S. So when you have x of S with S equal to j omega, you will get your x of omega. Okay. And after that, we looked at properties of your Fourier transform. For that, what we did, let's say you have one signal x of x1 of t, and it has Fourier transform as capital X1 of omega, and x2 of t, it has Fourier transform as capital X2 of omega. Then the first thing that you have is the linearity property. A1 x1 of t plus A2 x2 of t has a Fourier transform as A1 x1 of omega plus A2 x2 of omega. Then you have your time shift property. So x1 of t minus t naught has a Fourier transform as e power minus j omega t naught capital X of omega. In similar way, we have frequency shift property. So if you have e power j omega naught t x of t, x1 of t, this has a Fourier transform as capital X1 of omega minus omega naught. Then you have your time scale property. So if you have x of a t, then this thing has a Fourier transform as 1 over magnitude of a x of omega by a. Now, special case of this particular property is your time reversal property. So if you put a equal to minus 1, you get x of minus t, and that will give me magnitude of 1 minus 1 is 1, so x of minus omega. Then another important property is, or one of the important properties of your Fourier transform is duality property. So if you have x of t with Fourier transform as capital X of omega, now you flip the roles. You take the time domain signal as capital X of t. This thing is going to have a Fourier transform as 2 pi little x of minus omega. So this is the duality property. Then we looked at different differentiation in time. So d dt of x of t has a Fourier transform as j omega capital X of omega. Then we looked at differentiation in frequency. So if you have t into x of t, in frequency domain you get j d d omega of x of omega. Then you have convolution in time property. This is again gives you the interpretation of your system, LTI systems input output. So x of t, x1 of t convolved with x2 of t has a Fourier transform as x1 of omega into x2 of omega. And finally we looked at multiplication in time. So x1 of t into x2 of t, this will have 1 over 2 pi x1 of omega convolved with x2 of omega. Then we looked at the Parseval's relation. So Parseval's theorem or relation for a Fourier transform, continuous time Fourier transform, is basically integral minus infinity to infinity magnitude of x of t dt. This is basically energy of your signal, which is equal to 1 over 2 pi integral minus infinity to infinity magnitude of x of omega square d omega. Now you can get into the relation between your autocorrelation function and your energy spectral density. So energy spectral density is nothing but magnitude of x of omega squared. If you look at the correlation function or autocorrelation function, which is integral minus infinity to infinity x conjugate of tau x of t plus tau d tau, this is nothing but, this has Fourier transform as magnitude of x of omega square. Then we looked at the Fourier transform of an LTI system. So we have y of t as x of t convolved with h of t. So your y of omega, which is Fourier transform of your y of t, is nothing but capital X of omega into capital H of omega. So your transfer function of your system is basically transfer function of your output upon transfer function of your input. Then we looked at distortionless systems and transmissions, and then we looked at differential equation based characterization of your LTI systems. That is, you can just write it as d by dt of your input and output and different orders of different derivatives. And then we looked at ideal filters. So what is your ideal filter? So there are 4 classes of filters. The first one is your low pass filter. So low pass filter basically allows transmission of your low frequencies, or it passes the lower values of frequencies. So till some omega c and minus omega c. It allows everything to be passed. Otherwise, it just makes the signal zero. High pass filter does the exact opposite thing. Essentially does not allow the low values of frequencies to pass. A band pass filter allows the passing of a small band of frequencies like this, otherwise it is zero. So this is omega 2, omega 1, minus omega 1, minus omega 2. And band stop filter is the opposite of your band pass filter. So it rejects a particular band of frequencies and allows everything else to pass. So these are ideal filters. These are ideal in the sense that there is no transition band. But you have non-ideal filters, and for that the bandwidth is defined based on the 3 dB strength. So for what values of frequencies your maximum value, so this maximum value, so what happens is you get a filter which is something like this. So this is your 3 dB bandwidth, where at this particular value of your frequency or cutoff frequency, your signal strength drops to 3 dB. Then we looked at the band limited signal. So band limited signal is something that is whose Fourier transform is restricted to a particular small band, something like this. So the Fourier transform of that particular signal is non-zero only from minus omega m to omega m. For all other values of your frequencies, it is equal to, the Fourier transform is equal to 0. So that was all about the Fourier transform in the week 7. So that was introduction to Fourier transform and then looking at the properties of Fourier transform and all those things. Then in the week 8, we looked at something else, which is still related to your Fourier transform and continuous time Fourier series. So first thing that we looked at was this periodic convolution. So for periodic convolution, what we said that, let's say x1 of t and x2 of t, these are periodic signals with a common period as t naught. And let's say you have x tilde t, which is given by integral 0 to t naught x1 of t into x2 of t minus t naught t minus tau d tau. This is nothing but your periodic convolution. Then we said that if x1 of t has a Fourier series coefficients as AKs, x2 of t has Fourier series coefficients as BK, then this x tilde t, let's say it has Fourier series coefficients as CKs, then CK is nothing but T naught times AK into BK. So this is equivalent to your convolution property in Fourier transform. There you have a linear convolution. So a convolution translates to multiplication of Fourier transform. And in similar way, since you have periodic signal for Fourier series coefficients, the periodic convolution translates to your multiplication of Fourier series coefficients in the frequency domain representation. This is equivalent. Okay, then we looked at Fourier transform of some standard signals or interesting signals. The first one was this sine function. So this is defined as something like this. It is equal to 1 for t greater than 0. It is negative when its argument is negative, and it is half when its argument is equal to 0. And this particular signal has a Fourier transform as 2 by j omega. Then with the help of this particular transform, we found out the Fourier transform of your unit step function, which is pi delta omega plus 1 by j omega. Then we looked at the even and odd components of your Fourier transform. So for that, we said that any signal x of t can be decomposed into its even part and its odd component, where this xe of t is even signal and this xo of t is the odd signal. Okay. And let's say this x of t has a Fourier transform as x of omega, then this x of omega can be written as a real part a of j, this is real, a of omega plus j times b of omega. So this j times b of omega is completely imaginary. Then we said that, or we showed that your xe of t will have a Fourier transform as A of omega, and your XO of t, that is your odd component, will have a Fourier transform as J times B of omega. Then we looked at something known as Bode plot, and again this Bode plot is a way of finding or plotting an approximate phase response and magnitude response of a particular system. And this includes, so I'm not going to go into detail of how to do Bode plot and take examples here. You go to the week 8 tutorial content. We have taken ample amount of examples to understand that part. So this Bode plot, but I'll mention the steps. In order to obtain this Bode plot, there are 3 steps. So step 1, identify the corner frequencies. Then you have step 2, you obtain G of omega, which is equal to 20 log to the base 10 magnitude of H of omega for different regions between corner frequencies. And the step 3 is find theta h of omega, which is angle of H of omega for different regions. And at corner frequency. And step 4 is plot G of omega versus omega and theta h of omega versus omega. So this is all that was covered related to Bode plot. You can please go back and look at those examples that we have taken in that particular week's course, tutorial. Also, this is a standard thing that is done in the control systems course. So in case you have done that course, you should be accustomed to this kind of problems. Then we looked at another transform, which is known as Hilbert transform, H of t, which is 1 upon pi, which has impulse response H of t as 1 over pi t. And this particular thing has J sine omega. And we saw that in one of the examples that we saw in the week 8 tutorial, that this particular signal or transform is can be used to do phase changes in the signal, 90-degree phase changes in the signal, and it can also be used to generate the single sideband suppressed carriers and single sideband suppressed carriers and all those things. So we looked at those kind of things or applications of the Hilbert transform in that particular. Till this point, any questions at any point part of the tutorial?
No,
Okay.
ma'am.
Yeah, thanks. Okay. Then in the week 9, we continued our discussion related to ideal low pass filter. And for that, we looked at two quantities. The first one is your 3 dB cutoff frequency, which I mentioned in the previous thing. So filter that ideal filter that does not have transition bands, and we can't realize these ideal filters, so we go with RLC circuits and all those things, amplifiers and all those things to construct RC filters or RLC filters or some non-ideal filters. One example we saw was this RC filter, and we make use of this particular circuitry to get a non-ideal filter, and this non-ideal filter is characterized by multiple properties or metrics that govern the quality of this filter. and one is your 3 dB bandwidth, 3 dB cutoff frequency, that is omega 3 dB, and the third one is your rise time. So this rise time is the time taken by the output to rise from 10% of the final value to 90% of the final value. Or in other words, this T rise is equal to T 90% minus T 10%. And for an RC circuit, it is equal to RC log 9. All these derivations we looked at. And then we moved on to a very important concept of sampling of continuous time signals. So this sampling basically helps us to move from continuous time to discrete time. And the specific type of sampling that we looked at was the impulse train sampling. So in this particular sampling, what do? We consider a train of impulse in which an impulse is located at every integer multiple of your sampling duration, that is Ts. So Ts is your sampling duration, and your omega s is 2 pi by Ts is your sampling frequency. Okay, so how does this work? So this, let's say you have a time domain signal like this, and you have its equivalent frequency domain representation, which is something like this. Now you consider a train of impulse such that you have an impulse located at every integer multiple of your sampling duration Ts, and multiply it with your time domain signal. And this train of impulse has a Fourier transform of, again, a train of impulse delta Ts of omega, such that you have an impulse with height of omega s or area of omega s, and located at every integer multiple of your sampling angular frequency, that is omega s, 2 omega s, minus omega s, minus 2 omega s, and so on. So when you multiply this impulse with this particular signal, at every impulse, your impulse now picks up the area corresponding to the value of your actual signal at that particular time instant. So you get something like this. So here you start getting samples now at these locations. So you now get a discrete time signal. Now when you multiply this in frequency domain, you get convolution of this with this, as a result of which you get replicas of your original signal at every integer multiple of your omega s, like this. So you get something like this here. Now if you want to recover back your original signal, so remember, this was the Fourier transform of your original signal, but now you have replicas. So in order to just retain this particular block, what we can do is we can pass this particular signal through a low pass filter with a cutoff frequency which is more than this omega m, but which is less than this particular value of frequency. And if we do that, you get its equivalent representation in time domain is sync. We have seen that in the class. And then when you multiply this with this, you get convolution of this sync with this function. So you get sync replicas at every location of your impulse, and this is how you recover back your original signal or continuous time signal. So now what happens is, here the omega m is chosen such that it is less than your omega s minus omega m. But there might be a case such that your omega m, so this is your omega m and this is your omega s minus omega m. So if you don't choose omega s minus omega m, omega s properly, so and you get something like this or some sort of overlap or aliasing, then you can't recover back your original signal. So in order to recover back your original signal uniquely, you need to have your omega s minus omega m to be greater than or equal to omega m, so that we recover x of t back, which means that your omega s should be greater than or equal to 2 times your omega m, and this is nothing but your Nyquist sampling theorem. So now we move from our continuous time signals to discrete time signals. Now let us look at the series and Fourier series and Fourier transform for your discrete time signals. So first, let us look at your discrete time Fourier series. So let's say x of n is a periodic signal with period or fundamental period n naught. Then omega naught is the fundamental angular frequency, which is 2 pi by n naught. Then you can represent this x of n as summation k running from 0 to n naught minus 1 ck into e power j k omega naught n, and you can write the ck as 1 over n naught summation over n in any range n naught x of n into e power minus j k omega naught n. Then there are various properties of this Fourier series. First, it is guaranteed to converge. Is guaranteed to converge. Second, it is periodic. It is guaranteed to converge because it's a finite summation. Next, it is periodic with period, or rather, it is CKs are periodic with period and not. Then you have your duality property. So if x of n has Fourier series coefficient as ck, let's say it is given by some c of k, then if you look at c of n, which is again a periodic signal with period n naught, will have Fourier series coefficients as n naught into x of minus k. And finally, we have the Parseval's relation, which is given by, again, the preservance of energy or power. So this is equal to your summation running from 0 to n naught minus 1 magnitude of ck square. So this is the Parseval's relation that we have. So this is all about Fourier series coefficients for discrete time signals. So in the similar way, after looking at the continuous time Fourier series coefficients, we moved on to look at the continuous time Fourier transform. So now in the similar way, we'll now move on to look at the counterpart of continuous time Fourier transform for discrete time signals, which is your discrete time Fourier transform. Again, this is defined for, okay. Again, this is defined for aperiodic signals. So when you have your x of n, which is aperiodic, then its Fourier transform or discrete time Fourier transform is given by capital X of omega, which is equal to summation n running from minus infinity to infinity x of n into e power minus j omega n. And you can get back your x of n with 1 over 2 pi integral over a range of 2 pi capital X of omega into e power j omega n d omega. So this is your discrete time Fourier transform. Now this discrete time Fourier transform converges when your x of n is absolutely summable. Then it is related to your z transform as your x of omega is equal to your capital X of z with z evaluated at e power j omega. And this is equivalent to the case where both of them are equivalent to the case where unit circle is included in your ROC, belongs to your ROC. Then we started to look at the properties of Fourier transform. Just a minute. So for that, let us first take two signals, x1 of n. And let's say x1 of n has a Fourier transform as capital X1 of omega, and x2 of n has a Fourier transform as capital X2 of omega. Then the first property that we have is periodicity. So your x of omega is periodic, and yeah, x of n has periodic with period 2 pi. Then we looked at the linearity property. So a1 x1 of n plus a2 x2 of n has Fourier transform as a1 x1 of omega plus a2 x2 of omega. Then we have time shift property. So when you have x of n minus n naught, its Fourier transform is e power minus j omega n naught into x of omega. Again, you have frequency shift. So if you have e power j omega naught n x of n, this thing has a Fourier transform as x of omega minus omega naught. Then you have conjugation property. So conjugation property says that x conjugate of n will have a Fourier transform of x conjugate of minus omega. Similarly, you have time reversal property. So x of minus n will have a Fourier transform of x of minus omega. Then you have time scaling property. So to understand time scaling property, we first define a signal x m of n, which is equal to x n by m if n by m is an integer is 0 otherwise. So for that, now this x m of n has a Fourier transform as capital X of m of omega. Then you have duality property. Now this duality property basically relates your discrete time Fourier transform to your continuous time Fourier series. So if you recall, your capital X of omega is basically a periodic signal, but its domain is continuous. So the frequency domain axis is continuous. So therefore, but it is periodic with period 2 pi. So therefore, it relates your discrete time Fourier transform to your continuous time Fourier series. So what do you get? Is something like this. So if x of n has dtft as capital X of omega, then if you take capital X of t as a time domain signal, continuous time domain signal, and find its continuous time Fourier series, it will be equal to x of minus m, which is equal to your Cm. That is mth Fourier series coefficient. Then we looked at differentiation in frequency. So if you have n into x of n, then its Fourier transform will be equal to j times d omega of x of omega. Then you have time difference property. So x of n minus x of n minus 1 has a Fourier transform as x of omega into 1 minus e power minus j omega. Then we have accumulation property. So summation k running from minus infinity to n x of k has a Fourier transform as capital X of omega upon 1 minus e power minus j omega, but with an additional thing that takes care about the singularities and things, is pi x of omega into delta omega, x of 0 into delta omega. Then you have the important property, that is your convolution property. So x1 of n convolved with x2 of n has a Fourier transform as capital X1 of omega into capital X2 of omega. Okay, mind you that this x1 of n, x2 of n has nothing to do with this. These are these signals that we defined earlier. And then you have multiplication in time. So multiplication in time, x1n into x2n. We'll have x1 of n convolved with x2 of n, omega, whole divided by 2 pi. And finally, we have your Parseval's relation. So summation n running from minus infinity to infinity, magnitude of x of n whole squared. This is equal to 1 over 2 pi, integral over 2 pi, magnitude of x of omega squared d omega. Then we looked at LTI systems and differential equation characterization, and we also looked at how the Fourier transform of the differential equation looks like. And then we moved on to have an introduction to your discrete Fourier transform, but we didn't solve any questions related to that in that particular week. But discrete Fourier transform we focused more on in week 11. So till this point, do you have any questions? Okay. If not, then let me move on to the next part. So, okay. So why did we move from continuous time signals to discrete time signals? So we moved from continuous time signals to discrete time signals so that we are able to process them in our computers. Because our computers can't have your samples for each and every time instant. That is like infinite samples, it can't process. So we first need to sample them, and then we also do quantization. That is not a part of this particular course. We first need to understand what happens to your discrete time signals. Okay, so when we sample from continuous time to discrete time, we get discrete time signals. But if you look at the frequency domain representation of your discrete time signals, which is your discrete time Fourier transform, your omega is still continuous. So again, if you want to do frequency domain processing of your discrete time signals in your computers, you can't do it. So in order to enable that, what we did, we sampled the frequency domain as well. So what we did, we have your x of omega, that is your dtft, and then we sampled that 2 pi region. So your x of omega, you remember it is periodic with 2 pi. So it has a unique range of 2 pi. So you sample that unique range of 2 pi into n points, that is set omega equal to 2 pi k by n, and that will give me something known as x of k, where x of k is your n point discrete Fourier transform. So if you have x of n, which is a finite duration signal, you can find its n point discrete Fourier transform, which is x of k, and this x of k is given by summation n running from 0 to n minus 1 x of n into wn to the power kn, and you can recover back your x of n as 1 over n summation k running from 0 to n minus 1 capital X of k into Wn to the power minus kn, where this Wn is nothing but the nth root of your unity. So e power minus j 2 pi by n. So this is your n-point discrete Fourier transform. Now it is related to your discrete Fourier series. So let's say your x of n. So x of n, let's say it is some finite duration signal with duration less than your capital N. Now you construct another signal x tilde n, so that you repeat your x of n after every n time instance. So you make this x tilde of n as a periodic signal with period n, and in one period it is equivalent to your little xn. So in that situation, if your x tilde n has continuous time Fourier series coefficients at ck's, then your xk is nothing but n times your ck's. Another thing, your x of omega is periodic with period 2 pi, and you're sampling your signal there, signal in frequency domain. So when you're sampling it in frequency domain, you're not going to lose on your periodicity. So your xk's are also periodic, but now with a period of capital N. So that brings on to modulo operations in your time and frequency domain and everywhere. So now let us look at various properties of discrete Fourier transform. So for that, let's say x1 of n has an n-point DFT as capital X1k, x2 of n has n-point DFT as capital X2 of k, and let's say you have some x of n with DFT as capital Xk, again it is an n-point DFT. Okay, then the first property as usual is the linearity property. So a1 x1n plus a2 x2n has DFT as a1 x1k plus a2 x2k. Then you have time shift property, x of n minus n naught. Now sampling in one domain results in some inherent periodicity in the other domain, so that brings a wraparound effect in time domain as well. So you get some sort of periodicity there. So n minus n naught, but modulo n has, I'm not going into details of why this modulo comes, and it's discussed well in the lectures, minus j 2 pi n k n naught by n into x of k. And so then you have your conjugation property, x conjugate of n has a Fourier transform of x conjugate of minus k modulo n. It's a periodic signal, so it is going to repeat. Then you have frequency shift property. So you have e power j 2 pi k naught n by n into x of n. This thing has a Fourier transform as capital X of k minus k naught modulo n. Then you have your duality property. Just a moment. Yeah. Okay. Okay. So in duality property, if your x of n has an n-point DFT as capital X of k, and if you look at capital X of n, this will have the DFT as n times x of minus k modulo n. Then you have something known as circular convolution. So as I mentioned, you get some inherent periodicity and wrapping around impact effect by sampling in frequency domain. So there is a nice way of looking at this. Whenever you sample in one domain, you get periodicity that arises in its complementary domain. So if you sample in time domain, you had gotten replicas of your Fourier transforms in your frequency domain. So if you sample in frequency domain, you will start getting replicas in your time domain because you have convolution with impulses and all those things. You can go back and look at it in first principle sense. Okay, then you have, because of that periodicity, you have something known as circular convolution. Circular convolution is very similar to the periodic convolution that we saw for continuous time signals. I'll go into its details after some time. So x1 of n, when circularly convolved with x2 of n, will give me x1 of k into x2 of k, and this is some n point circular convolution. Okay. Then you have multiplication in time. So when you multiply in time domain, you get circular convolution in the frequency domain. N point circular convolution. And the last one, as usual, is the Parseval's relation. Okay, so summation n running from 0 to n minus 1, magnitude of x of n whole square is equal to 1 by n, summation k running from 0 to n minus 1, magnitude of x of k whole square. Okay, so these are all the properties of discrete Fourier transform. We looked at many questions related to discrete Fourier transform, and the last thing that concerns this particular thing is your circular convolution. So when you circularly convolve two signals, it is basically equal to k running from minus infinity to infinity. You have x1 of k, and in linear convolution, what you do, you flip the other signal and shift it by n units. Same thing we are going to do, but now instead of just shifting it by n units, we are going to have a wraparound, and that wraparound is going to be taken up care by the modulo operation. So x2 of n minus k modulo L. We just move it in this, move it a bit this side. Yeah. Yeah. So this is your circular convolution. So you flip the signal, shift it, and then you wrap whatever exceeds the value. Oh, sorry, 1 second. This is not minus infinity to infinity. This is 0 to n minus 1. Yeah. So whenever your n minus k modulo n exceeds n minus 1, you wrap it back to the range of 0 to n minus 1 and do multiplication and then additions. So we saw some examples of this circular convolution in the class. So just refer back to those examples. Try to solve questions which are related to this particular concept in various books. This convolution, circular convolution, its relation, how to get linear convolution from circular convolution, all of these things are important. These are like fundamental things that form basis of many courses that are going to come up in your future things. For example, this forms the basis of your discrete signal DSP, discrete signal processing, or rather digital signal processing course, or these frequency domain representations and all those things, sampling and everything is used widely in image processing concepts. It is used widely in your communication systems course and all those places. So this is a very basic and fundamental course for electrical engineering people as well as electronics and communication engineering people. So please take this particular course very seriously, as if you don't understand this at this point, the other courses in your higher semesters will become more difficult. Okay, so now let us move on to the last part, that is this last week's course, last week's content. So in this, we looked at only two topics. The first one was two types of delays, that is group delay and phase delay. And the other thing that we looked at was your um, system realizations. So you have your group delay, or rather, let's start with the phase delay first. So phase delay is tau p of omega naught. This is equal to minus phi of omega naught by omega naught, where phi of omega is angle of your h of omega. Where h of omega is the transfer function of continuous time signal. This is for continuous time systems. And then you have your group delay. So tau g of omega naught. This is minus d omega phi of omega, but now evaluated at omega equal to omega naught. And then you have, then we looked at another interesting thing. So if you have y of the output, which takes this particular form, cos of omega m t minus tau g into cos of omega naught t minus tau p. So this is basically like your message signal. This is like your carrier. You have your omega naught much greater than your omega m. So your message is affected by your group delay, and your carrier gets impacted by your phase delay. So this was all the discussion that we had related to your group and phase delays. And then we looked at the last part of this particular course, that is your IIR discrete time system realization. So what happens is you have your x of n, you have your output h of n, impulse response h of n, and you have your output y of n, and you get your transfer function h of z as y of z upon x of z, and this is given to you, and you want to realize h of z using some blocks. Given h of z, you have to realize it or implement this particular system. Now, in order to implement this particular system, we considered three blocks. The first one is your adder block. So x1n, then you have x2n. The output of this is basically x1 of n plus x2 of n. The second one is your gain block. So you have xn, output is g times x of n. And the last one is your delay block. You have x of n. This delay is represented using z inverse, and you get x of n minus 1. So you just based on these three blocks, we looked at 7 ways of doing your realizing this particular system. The first one was the direct form one. This is the naive way of doing stuff. So you write y of n as summation of scaled and delayed x of n plus summation of scaled and delayed y of n's. Write it like this and then realize this from the basic. Then you get your direct form 2 by swapping the two systems in your direct form 1. We did we did two examples of this on this Friday, so you can go back there and see it. Then you have direct form 1 transpose. In this, what you do, you have your h of z, which is nothing but y of z upon x of z. This you can write as sum w of z upon x of z into y of z upon w of z. So this is your h1 and this is your h2. So you realize h1 and you realize h2, put them in cascade and combine the common signal parts, common wires and all those things. That is this. And then similar to direct form 2, you swap systems in your direct form 1 transpose and combine the gain blocks and delay, sorry, not gain, combine the adders and delay blocks to get your direct form 2 transpose. Then we looked at cascade form. So cascade form and parallel form 1 and 2, these are the system realizations in which you have small blocks of already available systems. So how to do that? So if you are able to write your h of z as h1 of z into h2 of z, or maybe for that matter and so on till some hk of z, then you can represent this h of z as h1 of z, h2 of z, and so on till your hk of z. Then similarly, if you are able to write your h of z as summation k running from, or some l running from 1 to k hl of z, then you can get this as some h1 of z, h2 of z, and so on till hk of z, and add the outputs from all of these systems. Now, this parallel form can be constructed in using two approaches. One is parallel form 1 and another is parallel form 2. In parallel form 1, you do partial fractions in Z inverse, and for parallel form 2, you do partial fraction, like you map your h of z as only a function of z, there shouldn't be any z inverse term there, and get partial fraction representation in z, and then construct your h1, h2 and hk's and so on. So that's all that was covered in this particular week 12, and basically this was all that was covered in this particular course. So we started with very basic signals systems, classification of signals, then classification of systems, then we moved on to look at the Laplace transform that gave us some flavor of frequency domain representation. We looked at its counterpart, Z transform for discrete time signals and systems. Then we moved on to pure frequency domain representation. We first looked at the continuous time signals. In that, we first looked at the continuous time periodic signals that gave us continuous time Fourier series. Then we moved on to get frequency domain representation for your aperiodic continuous time signals that gave us our continuous time Fourier transform. We looked at the properties of these signals, these transforms. We saw how systems representation can be translated in frequency domain for continuous time signals. Then we looked at a concept of sampling that enabled us to move from continuous time signals to discrete time signals. And then we started to look at the frequency domain representation for our discrete time signals. Now in discrete time signals, we first looked at again the discrete time Fourier series coefficients representation. We looked at its properties and all those things, and then we moved on to discrete time Fourier transform to get the frequency domain representation of aperiodic discrete time signals. Then we said that, okay, hey, again, in the frequency domain, we don't have discrete values. We still get a continuous frequency representation. We can't process it again in our computer. So what to do? So in order to do that, we discretized the frequency domain as well, and that gave us something known as discrete Fourier transform. Then we looked at discrete Fourier transform and the circular convolution that comes with the notion of your discrete Fourier transform. We looked at its properties and all those things. And in the last week, we looked at the group and phase delays, how it impacts, and then given a transfer function, how can we realize a system physically or practically with the availability of these minimal three blocks, that is adder block, gain block, and delay block. So this is all that was covered in this particular course of 12 weeks. If you have any questions in any part of the course, please feel free to ask. That's all I wanted to cover today. And thank you for attending today's session, and thank you for attending all the sessions of these 12 weeks that I have taken. I hope this session was helpful. If you have any sort of feedbacks, then please let me know. Again, thanks. If you have any questions, please feel free to ask. Otherwise, you are free to leave the meeting. Thanks again.
Thank you, ma'am. Thanks a lot,
Yeah,
ma'am.
thank you.